Laser 1. Solid-state lasers. A solid-state laser produces light using atoms or ions embedded inside a solid material, usually a transparent crystal or glass. One of the earliest and most famous examples is the ruby laser, which uses a synthetic ruby crystal containing small amounts of chromium. Other solid-state lasers use materials such as neodymium-doped YAG, usually written as Nd:(YAG, which has become extremely important in industry, medicine, and scientific research. To understand what the solid material is actually doing, we first need the basic principle shared by almost every laser. An external source of energy excites atoms inside a material known as the gain medium. Electrons within those atoms move into higher energy states, and after some time they can return to lower energy states by releasing their excess energy as photons. Normally, these photons would appear at random times and travel in random directions. A laser changes this through a process called stimulated emission. If a photon with the correct energy passes an already excited atom, it can encourage that atom to release another photon with the same frequency, phase, and direction. One photon becomes two, two can become four, and the light becomes increasingly organized. The gain medium is usually placed between mirrors, forming what is called an optical cavity. Photons travel repeatedly through the material, stimulating more emissions each time. One of the mirrors allows a small fraction of the light to escape, producing the laser beam. In a solid-state laser, energy can be supplied using intense lamps or other lasers. The solid crystal can store considerable energy before releasing it, which allows some designs to produce extremely powerful pulses. Nd:(YAG lasers, for example, are used for cutting and welding materials, marking products, medical procedures, range finding, and laboratory experiments. The original ruby laser demonstrated the principle in 1960, but modern solid-state lasers can be far more efficient and powerful. Laser 2. Gas lasers. Instead of using a crystal, a gas laser uses a gas as its gain medium. One of the best-known examples is the helium-neon laser, usually called a He-Ne laser. Inside a sealed tube is a low-pressure mixture of helium and neon gas, with electrical energy supplied through electrodes. The electrical discharge first excites helium atoms. Those excited helium atoms collide with neon atoms and transfer energy to them, placing the neon into the energy states required for laser emission. Mirrors positioned at the ends of the tube then allow stimulated emission to build into an organized beam. The classic helium-neon laser produces red light at a wavelength of about 632.8 nanometers. It is not an especially powerful laser, but it can produce an extremely stable and narrow beam. This made helium-neon lasers useful in early barcode scanners, alignment systems, optical experiments, surveying equipment, and laboratory measurements. Gas lasers can use many different gases and produce many different wavelengths. Argon-ion lasers can produce intense blue and green light, while helium-cadmium lasers can operate at shorter wavelengths. Some gas lasers are designed for high precision, while others are intended for much greater power. The advantage of a gas is that the atoms can exist in a relatively uniform environment, allowing very specific electronic transitions to produce extremely pure wavelengths of light. Laser 3. Carbon dioxide lasers. The carbon dioxide laser is technically another gas laser, but it is important enough to deserve its own category because its behavior and applications are very different from something like a helium-neon laser. A CO2 laser usually contains a mixture of carbon dioxide, nitrogen, helium, and sometimes other gases. Electrical energy excites the molecules, and collisions transfer energy through the gas until carbon dioxide molecules reach the states needed for laser emission. Instead of producing visible light, carbon dioxide lasers mainly produce infrared radiation, especially around a wavelength of 10.6 micrometers. Human eyes cannot see this beam. However, many materials absorb this infrared radiation extremely well. When the beam is focused onto a small area, that absorbed energy becomes heat. This makes the carbon dioxide laser extremely useful for cutting, engraving, drilling, and processing materials such as wood, acrylic, fabric, paper, plastics, and some ceramics. The machine may appear to be simply drawing a line across a surface, but an invisible infrared beam is concentrating enough energy into that line to rapidly heat or remove the material. Carbon dioxide lasers can also be remarkably efficient compared with many older laser designs. They can operate continuously at significant power levels, which helped make them some of the most important industrial lasers ever developed. They have also been used in medicine, because water inside biological tissue absorbs their infrared wavelengths strongly. This allows energy to be deposited near the surface of tissue rather than traveling extremely deeply. So, although the CO2 laser operates through the same general idea of stimulated emission, its wavelength determines an entirely different set of useful applications. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. Laser 4. Semiconductor lasers. The laser inside a Blu-ray player, fiber optic communication system, barcode scanner, or laser pointer may be dramatically smaller than a gas tube or crystal laser. It can be a semiconductor laser diode. A semiconductor laser uses materials related to those found inside computer chips, although its structure is specifically designed to produce light. Instead of exciting isolated atoms inside a gas, electrons and positively charged vacancies called holes move through carefully engineered semiconductor layers. When electrons and holes recombine, energy can be released as photons. By designing the semiconductor so that large numbers of these photons stimulate further emission, the device becomes a laser. The tiny semiconductor structure itself can form part of the optical cavity, allowing the complete laser source to be only a fraction of a millimeter across. This small size completely changed laser technology. A laser no longer needed to be a large laboratory instrument containing a long glass tube, large mirrors, and a high-voltage power supply. It could become a tiny electronic component powered directly by electricity. Different semiconductor materials can produce different wavelengths. Red laser diodes became important for CD and DVD technology. Shorter wavelength blue-violet diodes enabled Blu-ray discs because their smaller wavelength could focus onto a smaller spot, allowing information to be packed more densely onto a disc. Semiconductor lasers are also fundamental to modern communications. In fiber optic networks, laser diodes can be switched extremely quickly, encoding digital information into pulses of light that travel through optical fibers. Billions of people therefore depend on lasers constantly without ever seeing the beams. Laser 5. Fiber lasers. A fiber laser takes another familiar optical technology and turns the fiber itself into the laser's gain medium. The active material is usually a very thin optical fiber whose glass has been doped with elements such as ytterbium, erbium, or neodymium. Another light source pumps energy into these atoms, and stimulated emission develops inside the fiber. The important advantage is that optical fibers are already extremely good at guiding light. Instead of allowing the laser beam to travel freely through a large cavity where alignment must be maintained carefully, the light remains confined within the narrow glass fiber. It can travel for long distances through the gain medium while remaining concentrated. This provides excellent efficiency and produces a beam that can be focused extremely precisely. The fiber also has a very large surface area compared with its volume, allowing heat to escape relatively effectively. Managing heat is one of the major difficulties in high-power lasers, so this geometry gives fiber lasers an important advantage. Modern fiber lasers can produce enough power to cut and weld metals while maintaining excellent beam quality. They are used throughout manufacturing to cut steel sheets, weld vehicle components, engrave serial numbers, manufacture electronics, and process extremely small components. Lower power versions are also important in telecommunications and scientific instruments. The strange part is that a fiber only slightly thicker than a human hair can form a central part of an industrial machine capable of cutting through metal. Laser 6. Dye lasers. Most lasers are designed around a gain medium whose atomic structure provides only certain useful wavelengths. Dye lasers approach the problem differently. Their gain medium is an organic dye, traditionally dissolved in a liquid solvent. These dye molecules have complicated electronic energy structures containing many closely spaced states. Because so many transitions are available, a dye laser does not have to operate at one fixed wavelength. It can be tunable. By changing components inside the optical cavity, researchers can select which portion of the dye's broad emission range becomes amplified. Some dye lasers can therefore be adjusted continuously across significant regions of the visible spectrum. This makes them extremely useful when an experiment requires a very specific color of light. In spectroscopy, for example, scientists study how atoms and molecules absorb particular wavelengths. A tunable laser can gradually scan across different wavelengths until it matches an exact atomic or molecular transition. Different dyes cover different wavelength ranges, so changing the dye can extend the available spectrum even further. The disadvantages are mostly practical. Liquid dye systems can be complicated. The chemicals can degrade under intense illumination, and some dyes and solvents require careful handling. Advances in solid-state and semiconductor lasers have replaced dye lasers in many applications, but their enormous tunability made them one of the most important technologies in laser spectroscopy and experimental physics. Laser 7. Excimer lasers. Excimer lasers operate using an unusual kind of molecule that is stable mainly while it is electronically excited. A typical excimer laser contains a combination involving a noble gas such as argon or krypton and a halogen such as fluorine or chlorine. Under ordinary conditions, these atoms do not strongly want to remain bonded together. After energy is supplied, however, an excited molecular state can temporarily form. When this excited molecule transitions downward and releases a photon, the lower energy state is poorly bound or completely repulsive. The molecule quickly separates again. This unusual energy structure makes it relatively easy to maintain the population conditions required for laser action. Excimer lasers generally produce ultraviolet light. A krypton fluoride excimer laser, for example, operates at a wavelength of approximately 248 nanometers, while argon fluoride produces even shorter ultraviolet light around 193 nanometers. These extremely short wavelengths are useful because they can interact with matter on very small scales. Excimer lasers became famous for their role in LSIK eye surgery, where ultraviolet pulses reshape the cornea by removing extremely thin layers of material. The process can remove material with relatively limited heating of the surrounding region compared with simply applying an intensely hot tool. Excimer lasers have also played a major role in semiconductor manufacturing. The 193 nanometer light from argon fluoride lasers became especially important in photolithography, where microscopic patterns are projected onto silicon wafers during the manufacture of computer chips. So part of the reason modern electronics contain features measured in nanometers is that engineers learned how to control extremely short wavelength laser light with extraordinary precision. Laser 8. Free electron lasers. The free electron laser is the type that stretches the definition furthest away from the familiar laser pointer. Most lasers rely on electrons bound inside atoms, molecules, crystals, or semiconductors. A free electron laser instead begins with a beam of electrons moving at nearly the speed of light. The electrons are produced and accelerated using technology similar to a particle accelerator. They then travel through a structure called an undulator, which contains a repeating arrangement of magnets. These magnetic fields force the high-speed electrons to move along a slightly oscillating path. Accelerating electric charges emit electromagnetic radiation, so the oscillating electrons begin producing light. Under the correct conditions, interactions between the electron beam and this radiation organize the electrons into microscopic groups. Their emitted waves then reinforce one another, producing an extraordinarily intense and coherent beam. The major advantage is tunability. Because the wavelength depends partly on the energy of the electrons and the properties of the undulator, free electron lasers can operate across wavelength ranges that are difficult for ordinary lasers to reach. Some facilities produce extremely short wavelength X-ray pulses. These X-ray free electron lasers are enormous scientific machines rather than small electronic components. Their pulses can be intense enough to investigate structures at atomic scales, and fast enough to observe processes occurring over incredibly short periods of time.